2 lectures ago, I identified some shortcomings of game theory. I focused on 3 in particular, dealing with payoffs, spontaneous equilibria, and rationality. Since then, we've seen some way that some of these shortcomings can be addressed. The problem of payoffs is a real one, but the problem isn't with the idea of payoffs. It's figuring out what the correct payoffs are. Psychology, sociology, and neurobiology are helping us to do that, to better understand how factors like a sense of fairness can modify our perceived payoffs. In fact, there's a whole new discipline, neuroeconomics, that's trying to replace the classical Homo economicus with something a little bit more like the real Homo sapiens. Our discussions of collective games suggested a way to address the spontaneous equilibrium problem. Players can periodically revisit and revise their strategies. The equilibrium behavior can evolve over time as a result of these choices. One can argue that this really means that the players are actually playing an iterated game that's perhaps different from the one-shot. Perhaps, but the choices that our players made in the last lecture didn't rely on the history of the game, only on the current state of society. Today, I'm going to take this evolution through time idea one step further. My topic is evolutionary game theory. It borrows from biology in its terminology and in its paradigm. This version of game theory rests on a different foundation than the one that we've developed so far. We're going to be getting rid of the requirement that the game be common knowledge. We're even going to be getting rid of the requirement that the players be rational. And in spite of this, we're going to see that many of the results that we've seen already are results that can be paralleled in the field of evolutionary game theory. So let's get started. I'm going to restrict my attention today to interactions between 2 members of an individual species. That simply means that the 2 individuals interacting will be drawn randomly from the same pool of contestants. But within this species, this population, different individuals may display different behavior patterns. The behavior patterns of a given individual is called its phenotype. This corresponds to its strategy in the traditional game theory. The difference is the phenotype isn't something that the individual can consciously choose. Phenotypes are hardwired. An individual can't change its phenotype any more than you can change your height. But a population may consist of entirely one phenotype, or it may consist of a mix. If all of its members have the same response patterns, they're all of the same phenotype. A population like this is called monomorphic, from the Greek meaning one form. Other populations may include 2 or more phenotypes. Each individual is hardwired to play a certain way, but different individuals might be wired differently. In a contest, one may be a hawk willing to fight for a prize, while the other may be a dove who's going to retreat from a fight. A population with multiple phenotypes is called polymorphic, many forms. How's this going to work? Well, imagine a population of 60% hawks and 40% doves. Pick one at random and watch its behavior. 60% of the time, it's ready to fight. 40% of the time, it's ready to run. Each individual is hardwired to either always play hawk or always play dove. But in watching encounters between members of this species, I see a species that acts like a hawk 60% of the time and acts like a dove 40% of the time. That is, together, the individuals in this polymorphic population behave like a person playing a mixed strategy. Actually, there's nothing to stop a single phenotype from being hardwired to use a particular mixed strategy. We could imagine a phenotype that, when confronted with a situation, acts as a dove 60% of the time and as a hawk 40% of the time. And what they act like is chosen randomly. You could then have a monomorphic population, all the same phenotype, but still see mixed strategy behavior. When we describe these things in terms of hawks and doves, we're seeing a mix. So monomorphic populations aren't the same thing as pure strategies. Okay, we've got our players, each with its own phenotype. Now, they interact. Pick 2 at random and play out their encounter. Each receives a payoff at the end. Sometimes the individual will have a good encounter, sometimes a bad one. But in evolutionary game theory, it's not the individual that we're really interested in. It's the phenotype. When a member of this phenotype encounters a member of that phenotype, on average, how do they do? In fact, we're really interested in even a larger question. How do members of this phenotype do in the population as a whole when compared to members of some other phenotype out there? To make this clearer, let me stick to my hawk-dove phenotypes. Let's say the population is only 10% hawks and 90% doves. How would we expect these phenotypes to fare? I'm a hawk. 90% of the people I meet are what you call doves. They back down, I get the prize. Good. 10% of the time, hawks. So, bada boom, we tangle. One of us gets the prize, one of us gets a busted beak. That's life. But, like I said, there ain't many hawks around, so life's good. How about a dove? Well, most of the time, I meet other doves, we don't fight or nothing, okay? Usually we kind of put on a show, try to get the other guy to back down, maybe. Sooner or later, somebody gets tired and leave, and that's a lucky day for the other dove. I guess I win my share. Of course, with a hawk now, forget it. Time to scoot. I don't win no prize, but I don't get no broken bones neither, you know what I mean? So, in a population that's 90% hawk and 10% dove, hawks get everything in 90% of their encounters at no cost. In 10%, they have a 50-50% chance of getting beaten up a bit or getting the prize. They get the prize 95% of the time and get beaten up 5%. Doves never get beaten up, but they get the prize only 45% of the time, half of 90, and they have to put on a show to do it. As long as the damage from a fight isn't too severe, it looks like the hawks have the better of the situation. And that means we'd expect hawks to grow at the expense of doves in this population. How well a phenotype does on average is called its fitness. It's the same idea as expected payoff in traditional game theory. Obviously, fitness depends on the mix of phenotypes in the population. When one phenotype is more fit than another, its proportion rises in the next generation of the population. In Darwin's theory, this is natural selection. When we're talking about evolutionary game theory, we're not necessarily talking about physical reproduction, though. Successful phenotypes aren't necessarily based on genes. With humans, for example, successful strategies may be shared with friends and colleagues, or those practicing unsuccessful strategies may change them to emulate those who did better. Whatever the mechanism, the effect is the same. The population proportionately ends up having more of whatever phenotypes were winners and less of whatever phenotypes were losers. Evolutionary game theory looks at the long-term results of what this will be. There are two common ways of asking the question, but they usually come down to the same thing. The first is dynamic. We start with a mix of phenotypes and let the population evolve over time. What's the long-term distribution of phenotypes going to be? The other approach is static. Suppose you start with a distribution of phenotypes that's stable over time. Can a small number of a different phenotype successfully invade that population? In all of my models, I'm going to assume a large number of individuals in the original population. It simplifies the math a bit, and it's usually realistic too. So, let's look at a simple example to get started. My population has two phenotypes. I'll call them Scrooge and Grim. The game that they're playing is a familiar one. It's a prisoner's dilemma. The Scrooge type always betrays. The Grim type betrays until it is betrayed, and cooperates until it's betrayed, and then it will betray from then on. It's playing a Grim trigger strategy. Mathematicians are interested in the model and technique rather than the particular example. And we're talking about a very general structure here. The players could be female vampire bats deciding whether to feed the young of other female vampire bats. Or it could be about plants deciding whether to release toxins around their bases, or any of a number of other applications. I'm going to cast it today as two employees from a company put together for a one-day project. They can either cooperate, or each can try to grab the credit. We're looking at a population where individuals meet, have one encounter, and then separate. Either they're likely to never meet again, or when they do, their histories don't make any difference. Maybe they don't remember, maybe they don't recognize each other. What happens in an encounter? Well, when two Scrooges meet, they both betray, so they both get 1. When two Grims meet, they both cooperate, so they both get 2. A Scrooge will betray a Grim, so the Scrooge gets 3 and the Grim gets 0. Since they only ever have one interaction, the Grim can never retaliate. So, what happens to this population of Scrooges and Grimms over time? Well, that depends on the mix. What fraction of the population is each phenotype? Let's call P the fraction of the population consisting of Scrooges. Then Grimms make up the remaining 1 minus P. So when an individual runs into another, the probability is P that that other guy is going to be a Scrooge, and 1 minus P that he's going to be a Grimm. Okay, now remember how we compute expected payoff. Probability times payoff added up over all the cases. So, what does all this tell us? Well, look at the average payoffs for the two types. The Scrooge, 3 minus 2p, is always bigger than the Grimm's 2 minus 2p, no matter what p is. That is, Scrooges are always more fit than Grimm's. So in the long run, Scrooges are going to wipe Grimm's out of the population. Scrooges breed faster, if you like. Once the Grimm's are gone, what happens when a few Grimm's from the next company over wander into this Scrooge population? Well, they're in big trouble, that's what. P would be almost 1, so the Grimm population would have a payoff of about 0, while the Scrooge payoff would be about 1. So the Grimm's would soon be wiped out again. That is, a population of all Scrooges can't be invaded by Grimm's. Evolutionary biologists call a population that can't be invaded by another phenotype an evolutionarily stable strategy, which they shorten to ESS. So we've just seen that an all-Scrooge population is an ESS. In fact, it's a monomorphic ESS, since the ESS includes only one phenotype, Scrooges. How about if we have an all-Grimm population? Then everybody cooperates. Happy day. Yeah. Until a few Scrooges show up, either from migration or from mutation. In a society that's almost all Grimms, P is close to 0. This means that a Scrooge has a fitness of about 3, and a Grimm has a fitness of about 2. Scrooges prey on the gullible Grimms and eventually take over. So a monomorphic Grimm population can be invaded by a few Scrooges. So a monomorphic Grimm is not an ESS. I've written a little spreadsheet application to show how this happens over time. This population started out on the left with 1% Scrooges. You can see they multiply at the expense of the Grimms. As the generations pass, their blue line goes up, and the Grimm's red line goes down and down. By generation 40, the Grimms are a fairy tale. Sorry. By the way, the actual number of generations that pass depends on a scaling factor in the model, but the shape of the curves is unavoidable. In fact, no matter what mix of Scrooges and Grimms you start with, as long as there are some Scrooges, you'll eventually approach an all-Scrooge population. Okay, let's stay with the Scrooges and Grimms, but imagine that they have encounters which last 2 steps, not 1. You can imagine that we're talking about them being paired with a coworker for 2 days. On each day, each worker can cooperate or grab the credit. Again, Scrooges always betray, Grimms will cooperate until betrayed, and then will betray after that. The new payoff matrix now looks like this. A Scrooge-Scrooge pairing will betray on both days, getting 1 point each day for a total of 2. A Grimm-Grimm pairing will cooperate on both days, each getting 4. When a Scrooge and a Grimm interact, on the first day, the Scrooge gets 3 and nothing for the Grimm, but then they both betray on the second day. Total payoffs, 4 for the Scrooge, 1 for the Grimm. Okay, what happens to this population? I'd like you to notice that both Scrooges and Grimms do equally well against Grimms. 4 points. Scrooges do better against other Scrooges than Grimms do, though. This means that if a society contains both phenotypes, the Scrooges will again outperform the Grimms, and the Grimms will again die out. Look at the expected payoff. Compare the two fitness functions. If there are any Scrooges at all, then P is bigger than 0. So Scrooges are marginally fitter. They grow a bit, and then a bit more, until eventually they trash the Grimms again. As before, Scrooges are a monomorphic ESS, and Grimms are not. It may take a few Scrooges a long time to wipe out the Grimms, but it'll happen. With our data, it took about 300 generations for the Scrooges to get to 20%. As you can see on the graphic, after that, it went fast. How can you spot one evolutionarily stable strategy, a monomorphic ESS? With only 2 phenotypes, it's pretty easy. We're talking about resisting invasion. If you're better at dealing with the population than the invader is, you're an ESS. If you tie the invader, but you're better at dealing with the invader than the invader is, then you're still an ESS. Otherwise, you can't repel an invasion and you're not a monomorphic ESS. Okay, let's carry the coworker problem one more day to a 3-day job. Then 2 Scrooges will betray 3 times in a row for 3 points. 2 Grimms will cooperate 3 days in a row for 6 points. When a Scrooge meets a Grimm, the first day it gets 3 to the Grimm's none, and then they both betray for 2 days. Final score, Scrooge's 5, Grimm's 2. Look at the fitness functions, the average payoffs. Who's fitter? Well, it depends. If P is small, not many Scrooges, then Grimms are better. Their fitness is just below 6, and the Scrooges is just below 5. But if P is large, lots of Scrooges, then Scrooges are better. Their payoff is a bit more than 3, compared to the Grimm's payoff of a bit more than 2. If you set these 2 fitness functions equal to one another, you find that they're the same when P equals 1/2. When the present number of Scrooges and Grimms is the same, they both have a fitness function of 4. So, in this evolutionary game, whoever has the majority at the outset wins. If there are more Scrooges, Scrooges take over and can't be invaded. If there are more Grimms, Grimms take over and they can't be invaded. Here are some sample graphs. The first one starts with 51% Scrooges. The second one starts with 51% Grimms. And what happens when exactly 50% of the population is Scrooges? Then both sides are equally fit, and so the 50-50 split persists. It's an equilibrium. But it's an unstable one. A tiny nudge from the outside, one way or the other, a migrant, a mutant, will start a cascade to one of the 2 monomorphic ESSs. So we don't call this 50-50 mix an ESS, because it's not stable. Could you ever have a polymorphic ESS, more than one form coexisting but in balance? To look into this, I'm going to go back to our friends from the earlier lecture, the hawks and the doves, earlier in the lecture, the hawks and the doves. I'll put some numbers to this. To make it specific, suppose that 2 individuals are in a contest for a prize worth 50 points. If they're both hawks, they fight until one's hurt and the other's victorious. Let's say the injury costs the loser 80 points. When a hawk meets a dove, nothing to talk about. The hawk gets the 50 points and the dove gets nothing. When 2 doves meet, each puts on a display trying to convince the other one to give up. Eventually one quits, and the other one wins the prize. Both doves pay the same display cost, though, until the show's over. Let's say the display cost is 10 points on the average. You could imagine, for example, 2 job applicants at a reception, each waiting for the other one to leave so that they could get the last word with the recruiter. Both pay the waiting cost until the loser leaves. Okay, let's clean up the matrix to show the expected payoffs. Half of the time the hawk gets 50, and half of the time it loses 80. So her average payoff against a hawk is half of 50 plus a half of negative 80, or negative 15. When 2 doves meet, half the time the dove wins, getting 50, and half the time it loses, getting 0. That's 25 on average. But win or lose, the dove pays the display cost of 10. So the average payoff to a dove in a dove-dove meeting is 15. And of course a hawk gets everything and a dove nothing in a hawk-dove encounter. Okay, check the matrix. Who does best when meeting a hawk? Doves do. A hawk on average loses 15. A dove gets nothing when it meets a hawk, but that's better than negative 15. Who does better when meeting a dove? Hawks do. Hawks get 50 points for meeting a dove, while doves on average only get 15. So what? So, when there are a lot of hawks around, it's best to be a dove. And when there are a lot of doves around, it's best to be a hawk. Look at the fitness functions. Sure enough, if P is small, not many hawks, then hawks are more fit. If P is big, lots of hawks, then doves are more fit. Set these 2 equal and you'll find out that they come out to be equal when P is 0.7. If the population is 70% hawks, then both hawks and doves are equally fit, a fitness of 4.5. You can see this borne out in the graphs. I've started with lots of hawks, then lots of doves, then equal numbers of both. No matter how the population starts, it quickly approaches the polymorphic ESS of 70% hawks and 30% doves. Okay, let's stop for a second. I want to see how our new work compares with the work from earlier in the course. Here's our matrix for the first game. We found today that the only ESS for this game was monomorphic Scrooge. But suppose I'd given you this matrix before today. You'd say it's a two-player, non-zero sum, simultaneous game. How would you solve it? Well, look for dominant strategies. For both players, the Scrooge strategy dominates the Grimm one. Each player is always better off playing Scrooge, so the only Nash equilibrium in this game is Scrooge-Scrooge. That is, everyone's playing Scrooge all the time. And that's exactly what we see when we say that the only ESS is monomorphic Scrooge. How about the two-day game? Now Scrooge weakly dominates Grimm. There are two Nash equilibria, Scrooge-Scrooge and Grimm-Grimm. But you'll recall in working with simultaneous games that we often restricted ourselves to admissible equilibria, ones that weren't weakly dominated by anything else. And there's only one such equilibrium, Scrooge-Scrooge, with everyone playing Scrooge all the time. And that's also the only ESS of this game, monomorphic Scrooge. I think you're getting the idea, but let's go on. Three-day matrix. This game has three equilibria. Two are admissible and impure strategies, Scrooge-Scrooge and Grimm-Grimm. You'll recall that in this game, Scrooge was a monomorphic ESS, and so was Grimm. We can find the mixed equilibrium in the traditional game by solving our usual equations or doing the usual tricks. I'll leave that to you. If you do it, you'll find out that the equations that you're solving are exactly the ones that we computed in finding average fitness. The mixed equilibrium strategy has each player playing each choice half the time. In the evolutionary game, we saw an equilibrium when the population was divided between Scrooges and Grimms, but it was unstable. In a tiny imbalance between the types set the population all in one ESS or all in the other. Clearly, we're seeing a strong connection between equilibrium behavior in traditional game theory. And evolutionarily stable strategies look a lot like optimal strategies. Let's look at hawks and doves. To get our full complement of birds in this lecture, I'll point out that the game that the hawks and doves are playing is really chicken. Each player decides to choose the option not chosen by the other. This game, too, has three equilibria. In pure strategies, hawk-dove and dove-hawk. And in a mixed strategy, 70% of the time hawk and dove the rest of the time. Average payoff for that one is 4.5. How does this match up with the evolutionary approach? Well, row playing hawk while column plays dove doesn't make sense in our evolutionary model, not all the time. The two players are drawn from the same population, one species, remember? So the population can't be all hawk and all dove. So the only physically meaningful equilibrium in this problem is the one which has us playing hawk 70% of the time and dove 30%. And the only ESS for this game is the polymorphic population of 70% hawks and 30% doves. It may seem to you that we're just covering the same ground that we did much earlier in the course. If so, look again. Yes, we are getting the same answers. We're seeing a strong correspondence between Nash equilibria on the one hand and the ESSs of evolutionary games. But there are some important differences. And here's the biggest. We never required the players to be rational. We didn't even require them to know the payoff matrix. In the evolutionary model, a phenotype grows because it works. No one consciously has to choose it. It's easy to show that any ESS is a Nash equilibrium, but we arrive at it without requiring players to compute probabilities or strategies. There aren't even any probabilities to compute. Remember, each of our individuals is hardwired to their phenotype. They're not choosing anything. What we've been looking at so far is dealt with symmetric games. The two players face exactly the same situation. It's not necessary to have that for the evolutionary approach to work. If we draw the players from two different species, then they can have different choices, or they can have different probabilities in the population. The battle of the sexes can be handled in this way, for example. If you're curious, there are two ESSs in the battle of the sexes. One in which men always do what they want, and the women always go along, and one in which the women always do what they want, and the men always go along. And if you think I'm going to make any comments about that, you are out of your mind. You can handle as many different phenotypes as you want. And this brings up a clarification I need to make. I told you that evolutionarily stable strategies can't be invaded by another phenotype, and this is true, but only within the context of the phenotypes possible, the options that exist within a game. In the 3 Days Scrooge Grimm game, both Scrooge and Grimm were monomorphic ESSs. Once established, they were both bulletproof from the other phenotype. But I could introduce a new phenotype in this game. Let's call it a sneak. A sneak plays just like a Grimm, but always betrays on day 3. This new type, it turns out, can invade an all-Grimm population. So in a universe of Scrooges, Grimms, and sneaks, Grimms are no longer an ESS. Only Scrooge is. You can get some pretty complicated behavior in such systems. Think about it. Scrooge can't invade Grimm, but Sneak can. And it turns out that Scrooges can invade Sneaks. So start out with a population that's almost all Grimms, but season it with a few Scrooges and Sneaks. The Sneaks will eat the Grimms and prosper, while the Grimms dwindle. Then the Scrooges will eat the Sneaks. By the way, if you analyze the payoff matrix for this game, you'll find that there's only one admissible equilibrium in the game: Scrooge. Like the rest of game theory, evolutionary game theory gets quite deep. The mathematics behind it can get rather sophisticated. I'm not going to develop the math for this last example I'm about to do. It requires integral calculus. But I think you'll find the results interesting. The game is commonly called the War of Attrition. There are lots of ways to think about this game. As the name suggests, you can have a war for a prize going on in which both sides are suffering losses until one side gives up. The problem, of course, is that one can end up with a Pyrrhic victory. You pay more for the win than the value of the prize. We could imagine a war of attrition in nature. Two animals could make an aggressive display without actually fighting until one gives up. Think about the mating behavior of a lot of species. Remember when I told you about the $100 auction when it went for $465 to the Wall Street financiers? That's an example. The winner and the second place bidder both had to pay their bids. It'd be a war of attrition if they both had to pay the winning bid, but only the winner got the $100. Something similar, but more complicated, goes on in the Olympics, assuming that the gold medal is the only reason to train. Everyone pays the training cost, but only one person gets the prize. To fix ideas today, I'm going to focus on the example of the $100 bill auction. I'll conduct it a little differently. Both players are given a buzzer. At the beginning of the auction, the clock starts counting from $0 upward. When someone buzzes in, the clock stops. The person who pressed the buzzer loses. The other player gets the $100, but both players must pay the money shown on the clock. If they both buzz simultaneously, they both get half of the $100. Well, there is a Nash equilibrium for this game. One player buzzes immediately, and the other wouldn't buzz until after 100. This equilibrium requires that the two players coordinate and adopt different strategies, essentially decide who's going to be the winner. They may have a tough time agreeing on this. The evolutionary game theory analysis of this game is quite interesting. A phenotype is specified by how long it's willing to compete before quitting, the dollar amount at which it'll push the buzzer. We're looking for evolutionarily stable states. Can there be a monomorphic one that can't be invaded? Well, suppose that a monomorphic population pushes the button at something less than 100, 90, say. Now imagine an invader that waits just a little bit longer, say 91. Then the invader wins every contest against the member of the population, because the population always pushes at 90. The invader's payoff is therefore $10 against any member of the population. It gets 100 and pays 90. The average payoff of one 90 pusher against another is negative 40. They both pay 90, but only get half of the 100, which is 50. So a monomorphic population that pushes before 100 can be invaded by someone who pushes just a little later. Okay, how about a monomorphic population that pushes in sometime later? Let's say after 50. 90, for example. Well, imagine an invader who buzzes immediately. This player gets a payoff of 0, which isn't that great. But a member of the population playing against another member of the population does worse. Again, if I buzz in at 90, and you do too, we both get 50. That puts us both 40 in the hole. That's worse than buzzing in immediately and getting 0. So this phenotype can be invaded by someone who presses immediately. A population that waits more than 50 can be invaded by buzzing immediately. A population that buzzes in before 100 can be invaded by one that waits a little longer. So there are no monomorphic ESSs for the war of attrition. But there is a polymorphic one. You could think of the optimal strategy as being essentially this. Each time that the dollar clock clicks one more dollar, give yourself about 1 chance in 100 of buzzing in. The actual chance should be 0.995%. For example, generate a random number from 1 to 100, and if it's 100, buzz in. If not, wait until the next dollar and do the same thing. You'll note there's a chance that you actually won't buzz in before 100. That's okay. You can show mathematically that this strategy outperforms any monomorphic strategy, any fixed stopping point, by at least $19 on average. Wild, huh? Maybe we should tell Wall Street.